A man on a stage once pointed a laser at the Maeslantkering and called it the Great Wall that holds back the sea. The room nodded, because that's the story everyone already believes about the Dutch. Sea on one side, land on the other, and between them a wall, the bigger the better. I remember thinking that almost every word of that sentence was wrong. The structure defending one of the most valuable stretches of land in Europe isn't a wall. It isn't solid, and for most of the year, it isn't even in the way. The Dutch had every reason to build a permanent barrier here, and they deliberately chose not to. It sits at the mouth of the new Waterway, the shipping channel that runs inland to Rotterdam, the largest seaport in Europe, moving over 400 million tons of cargo in a typical year. A fixed dam across that channel would protect the land behind it and choke the economy in front of it at the same time. So the engineers were handed a contradiction. Stop the worst storm in 10,000 years, and the rest of the time, stay completely out of the way of the ships. You can't do that with a wall. You can only do it with a machine. They knew exactly what getting it wrong looked like. On the night of the 31st of January, 1953, a North Sea storm surge broke through the old dikes while people were asleep. More than 1,800 people died in the Netherlands in a matter of hours. Around 9% of the country's farmland went under saltwater, and tens of thousands were driven from their homes in the dark. Behind that one channel lies a country where roughly a quarter of the land sits below sea level, and more than half is vulnerable to flooding. The answer was the Delta Works, decades of dams and barriers built to a single unforgiving standard. Survive the surge that comes once in 10,000 years. The Maeslantkering was the final piece, finished in 1997, and it was the hardest because it guarded the one channel they were never allowed to close for good. So look at what they actually built. 2 hollow steel gates, each curved like the hull of a ship laid on its side. Each gate wall runs about 210 meters long and 22 meters tall, and the curve isn't decoration. When the sea pushes against a curved gate, the arc turns that horizontal pressure into compression running along the steel, carrying the force back through the arms and into the foundations on the bank instead of trying to snap the gate in half. To hold that shape under load, the gates are stiffened inside like the ribbed hull of a ship, hollow but braced against buckling. Behind each gate, a steel truss arm carries the force to the shore, and each arm reaches about 237 meters, longer than 2 football pitches end to end. Together, the 2 gates and their arms hold something like 13,000 tons of steel, close to twice the iron in the Eiffel Tower. They rest in dry docks on either side of the channel, waiting. And here's what the man with the laser pointer never mentioned. All that steel, both gates, the entire defense of a city below sea level, pivots on 2 joints. Each arm meets its foundation through a single ball and socket joint, the same idea as your hip, scaled up until each ball is about 10 meters across and weighs around 680 tons, cast in sections and assembled into one sphere. They're reported to be among the largest ball joints ever built, and the shape wasn't a preference. A hinge moves on one axis. This gate has to swing out across the water, then sink straight down onto the riverbed, while waves shove it from the side, load arriving from every direction at once. Only a ball can carry force from every angle at the same time, so the designers took all of that curved gate pressure, ran it down the arms, and concentrated it into 2 steel spheres. Everything the barrier is asked to do passes through those 2 points, which creates a strange, permanent problem. A joint that carries the safety of a below sea level nation sits in salt water, has to resist corrosion year-round, and gets asked to actually turn perhaps once a year, and it has to be certain to move on the one night it matters. You already trust points exactly like these. The bolt holding your wheel to your car, the brake in the elevator you rode this morning. Modern life runs on small parts we've decided are strong enough that we never think about them again. The Dutch did the same thing. They just made theirs the size of a house and bet a country on it. This channel is really about systems like that one, the machines running quietly under modern life that almost no one thinks about until the day they fail. If you want more of them, subscribe, and I'll keep finding them. Most of the time, nothing happens. The barrier is built for a storm expected once in 10,000 years, so for long stretches, it simply waits. A few €100 million of steel and concrete. 1 full test closure every autumn to prove the joints still turn, and otherwise stillness, holding position for a single night that might not come for a decade. Then the forecast turns. The 2 dry docks flood, and because the gates are hollow, they float. No tugs, no cables. The gates drift out under their own buoyancy, one from each bank, until they meet in the middle of a channel about 360 meters wide. Valves open, and hundreds of thousands of tons of water pour into the hollow gates until they lose their float and begin to sink, settling down onto a concrete sill lying on the seabed. That sill is its own feat, a foundation dredged and graded flat across the floor of a working shipping channel, level enough that two moving gates the length of skyscrapers can seat against it and seal, in the dark, in the storm, with the full North Sea pushing on the other side. The whole sequence from resting in the dock to sealed against the bottom takes about 2 hours, and every ton of that force runs back through the two joints on the bank. No person gives the order to close it. The Maeslantkering is run by a computer system the Dutch call the Decision and Support System. When the forecast shows the water climbing toward roughly 3 meters above the national reference line they call NAP at Rotterdam, the system decides to close, on its own. Operators watch. Backup systems and independent forecasts feed it, and a human can step in if something is clearly wrong. But the choice to seal off the approach to the largest port in Europe is made by software, deliberately. The engineers built it that way because a surge arrives on the water's schedule, usually in the middle of the night, and the call has to be made hours ahead, on a prediction, at exactly the moment a person hesitates, waits for one more forecast, worries about shutting the port for a storm that might weaken. They looked at that hesitation and decided the human was the least reliable part of the whole machine, so they took the human out. The first time the system closed the barrier for a real storm, on the 8th of November 2007, it worked exactly as designed. It's done it again since, in 2018, and as the seas rise, that once-in-a-decade assumption is starting to look optimistic. No one told it to close any of those times. So I think back to the man with the laser pointer, circling the gates, saying, "Wall." He was looking at the most visible thing and describing it backwards. It isn't a wall, because a wall would have killed the port. It isn't solid, because it has to float before it can sink. And when the night finally comes, no one on any stage, and no one at all, gives the word. Two steel spheres take the load, the software makes the call, and at the mouth of the new waterway, with no hand on it, the gate swings shut.